Hello everyone, I am Honar Gupta, currently a PhD scholar at IIT Kanpur. Today we will discuss week 10 of the course Fundamentals of Supersonic and Hypersonic Flow. We will solve some problems of week 9 assignments and then we will solve problems of week 10. Some problems for week 10 and some theory. We'll see the first problem. A frozen flow satisfies the following characteristics. Pick the correct option or options. Option A. Forward and backward reaction rate constants are both 0. Option B. Forward and backward reaction rate constants are finite and non-zero. Option C. Vibration relaxation time is 0. Option D. Vibration relaxation time tends to infinity. So what will be the answer for this problem? So for frozen flow, is such that the chemical reaction does not happen in frozen flow, and vibrational relaxation, there is no vibration. Vibrational reaction time also tends to infinity. So tau tends to infinity, and forward and backward reaction rate both will be equal and both will be equal to 0 because there is no chemical reaction happening. Or it can be said like this, that flow is so fast that chemical reaction does not get time to happen. So in this problem, answer will be option A, where both forward and backward reaction rates constants are 0 and vibration relaxation time tends to infinity. Now we'll see the next problem. Equilibrium flow has the following characteristics. Pick the correct option or options. Consider tau as the vibrational relaxation time. Option A, Kv equal to Kf tends to 0. Option B, Kv equal to Kf tends to infinity. Option C, tau tends to infinity, and option D, tau equal to 0. So for the equilibrium flow, chemical reactions are so fast that in the flow from one point to another point, there will not be any non-equilibrium characteristics. So flow will attain equilibrium instantaneously. So for this to happen, the chemical reaction rate should be infinite, and the vibration relaxation time should also be equal to 0. So correct option will be option B, Kv equal to Kf tends to infinity and tau equal to 0. We'll see the next problem. In the context of non-equilibrium effects in connection with vehicle dimensions and flight altitude, choose the correct option. Tau F is flow time and tau C is chemical reaction time. Statement 1 is tau f upon tau c becomes small for smaller bodies and higher altitude leading to non-equilibrium effects. Statement 2, tau f upon tau c becomes large for bigger bodies and lower altitude leading to equilibrium flows. Option A, statement 8, 1 true, statement 2 true. Option B, statement 1 false, statement 2 true. Option C, statement 1 true, statement 2 false. Option D, statement 1 false, statement 2 false. So in this problem, there are two statements are given which are related to non-equilibrium effects in connection to vehicle dimension and flight altitude. And we have to tell which statement is true and which is false. So what will be the answer for this problem? We will see. So in first option, it is given for smaller bodies and high altitude. Smaller bodies and higher altitude. So it is the ratio between tau f and tau c. And tau f depends on, this is the flow time. So flow time will depends on the characteristics length, and if body is small, then characteristics length is small. So this tau f will be small for smaller bodies, and for the high altitude, density will be low. So due to the low density, there will be low collision frequency. So due to the low collision frequency, the chemical reaction time will be less. Sorry, chemical reaction time will be high. So as this tau c is high and tau f is low, that's why this value will be small for smaller bodies and high altitude. So this statement that tau f and tau c becomes small for smaller bodies and high altitude, leading to non-equilibrium effect. And we have seen that tau f is, this value is small. So this value is small means that the chemical reaction time is higher than flow time. And if this is the case, then there will be, it will lead to non-equilibrium, because chemical flow in between the flow time itself, chemical reaction is still happening. That's why there will be non-equilibrium. So this statement will be true. In the second statement, it is for bigger bodies and lower altitude. For bigger bodies and lower altitude. Sorry, this is altitude. Tau f and tau c. For bigger bodies, tau f will be high because of the characteristics length, and tau c at a lower altitude, density will be higher compared to higher altitude. So it will have high collision frequency, so tau c will be lower. So at tau f and tau c will be large for this case. It will be large, and if this value is large, then chemical reaction are happening faster than the flow time. So flow will be have the equilibrium flow. So this statement is also true, which says tau f and tau c becomes large for bigger bodies and lower altitude, leading to equilibrium flows. So both statements are true. So option A is the correct option. Now we will see the next problem. Let rho I be the instantaneous value of mass of species I per unit volume of the gas mixture that exists for high temperature air under non-equilibrium. If we consider a control volume where Wi is local rate of change of rho I due to chemical reaction occurring inside the control volume, then the continuity equation for species I would be as follows. Often dou rho I upon dou t plus rho I del dot v vector equal to Wi dot. Often be dou rho I upon dou t plus del dot rho I v vector equal to 1 upon Wi. Often see dou rho I upon dou t plus del dot dou rho I del dot rho I v vector plus Wi dot equal to 0. Often D dou rho I upon dou t plus del dot rho I v vector equal to Wi dot. So we have to tell the species continuity equation. So which one will be the correct equation? So the correct equation is option D, which says dou rho I upon dou t plus del dot rho I v vector equal to Wi dot. Now we'll see the next problem. When we consider a non-equilibrium chemical reacting air mixture where there are 10 species, choose the correct option for the following statement. Statement 1. 9 species continuity equations along with equation sigma I equal to 1 to 10, rho I equal to rho, where rho is mixture density, has to be solved. Statement 2. 2 species continuity equations have to be solved of the form dci upon dt equal to rho Wi dot. Option A, statement 1 false, statement 2 false. Option B, statement 1 true, statement 2 true. Option C, statement 1 true, statement 2 false. Option D, statement 1 false, statement 2 true. So statement 1 says that. So what will be the correct answer for this? Okay, we'll see the what will be the answer. So statement 1 says that we have to solve 10 equations in which one is sigma I equal to 1 to 10, rho I equal to rho, and other are dou rho I upon dou t plus del dot rho v vector equal to Wi dot. We have seen it before, this species continuity equation. This one. So these for 9 species and one this. This is the correct statement. We use this because if we use all 10 this species continuity equation, there might be some error because it may not satisfy this criteria, because this is one constraint of the equation. If this constraint is not satisfied, then equation will be, the solution will be incorrect. Statement 2 says 10 species continuity equation have to be solved of the form dci upon dt equal to rho wi dot. First thing which I already told that we don't solve 10 species continuity equation. We use one constraint sigma I equal to 1 to 10 rho I equal to rho. And second thing is that the correct form of equation is dci upon dt equal to wi dot upon rho. And this form itself is wrong, that's why this statement will be false. So correct option will be option C, which says statement 1 true and statement 2 false. Now we will see the next problem. Choose the correct option or options from the following statements about vibrational energy exchanges in the high temperature air. Statement 1. The vibrational rate equation for a moving fluid element in a non-equilibrium flow is given by dE vibrational upon dt equal to 1 by tau E vibrational equilibrium minus E vibrational. Statement 2. A nearly equal number of molecular collisions are required for chemical reaction and vibrational excitation to occur. Statement 3. For some situation, the molecular collision frequency may be high enough to lead to vibrational equilibrium, but not high enough for chemical equilibrium. Option A, statement 1 false, statement 2 true, statement 3 false. Option B, statement 1 true, statement 2 false, statement 3 true. Option C, statement 1 true, statement 2 true, statement 3 true. Option D, statement 1 false, statement 2 true, statement 3 true. So this problem is related to vibrational energy exchanges in high temperature air. There are 3 statements are given and we have to tell which one is true and which one is false. So what will be the answer for this problem? Okay. First we will see statement 1, which says vibrational rate equation for moving fluid element in non-equilibrium flow is given by this equation. If you see this equation, this is the correct equation. d E vibrational upon dt equal to 1 by tau E vibrational equilibrium minus E vibrational. This is a true. So this is the true statement. Statement 2. A nearly equal number of molecular collisions are required for chemical reactions and vibrational excitation to occur. Before solving this statement, I will tell this third statement. For some situation, the molecular collision frequency may be high enough to lead to vibrational equilibrium, but not high enough for chemical equilibrium. So we already know that for chemical reaction to start, we need some extra energy to breaking the bond. So bond will only break when we have that sufficient energy. So for breaking that bond, we might need more number of molecular collision than required for the vibrational equilibrium. So you can see that this statement is true. And if this statement is true, then from statement 2 you can see that it says that a nearly equal number of molecular collisions are required. So we have already seen that it might be high also for the chemical reaction to occur. So this statement is false. So if we check the options, then option B will be correct. Now we will see the next problem. A strong attached oblique shock is formed when high velocity air flows past a slender wedge inducing chemical reaction of the dissociation kind. Choose the correct option in this context. Statement 1. Normal component of the velocity downstream of the oblique shock wave increase behind the shock. Statement 2. Straight oblique shock can form on a curved surface, which accounts for curved streamline behind the oblique shock. Statement 3. A curved oblique shock will form on a straight wedge surface. So, option A, statement 1 false, statement 2 true, statement 3 true. Option B, statement 1 true, statement 2 false, statement 3 true. Option C, statement 1 false, statement 2 false, statement 3 true. Option D, statement 1 false, statement 2 false, statement 3 false. So this problem is related to a test oblique shock, which is formed when high velocity air flow past the cylinder wedge and there is chemical reactions are happening. And we have to tell which of these three statements is true and which one is false. So what will be the correct answer? Okay, we will discuss now. So first thing to know that according to the governing equation, rho1 u1 n equal to rho2 u2 n. So if density increases, then velocity will, and if you see these plots, then across the normal shock, the density increases. So if density is increasing, then normal velocity will decrease. So the statement 1 which says that normal component of velocity downstream of the oblique shock increases behind the shock. It is false because it always decreases. Now this plot we have already seen before in the discussion session. So if generally behind the shock there is very thin region, first thin region which is where flow is frozen, then small region when flow is non-equilibrium, then the region which is in equilibrium. So initially across the shock, for the very small region, the flow will be frozen, so temperature will be equal to frozen temperature. After that, due to this high temperature, there will be more number of collision, so there will be vibrational and chemical non-equilibrium. Due to this vibrational and chemical non-equilibrium, some of the translational energy will go to these modes. So as translational energy is going to this mode, so temperature will decrease, and it will decrease till the equilibrium is attained, and we will get one temperature will be equal to T equilibrium. And the temperature will mainly also decrease because there is dissociation is happening. So in dissociation, energy is required. So energy is lost only from the translation energy. And if we see the density now, so if temperature increases, then density decreases. So here the temperature is decreasing. Temperature is decreasing in the non-equilibrium region, so density will increase. Now we will see what happens across a straight oblique shock. So let's say this is the straight oblique shock, and we know that the flow across a tangent does not change. So tangential velocity will be same everywhere. and across a normal to the velocity decreases. We have already seen rho 1 Vn1 equal to rho 2 Vn2. So just after the shock, as will be frozen, so its velocity will be high, normal velocity. But as we move away from the flow, due to the non-equilibrium, the density rho 2 will decrease. As rho 2 is decreasing, sorry, this is a mistake. As rho 2 will increase, we have already seen from this plot, as rho 2 will increase, this Vn2 will decrease. As this Vn2 is decreasing, and if you see this figure, this Vt2 will be the same everywhere, but this Vn2 is decreasing. If this Vn2 is decreasing, then this angle theta 2 will increase. So as we are moving away from the shock, then theta 2 is increasing. So the streamline will be a curved streamline. So on a curved surface, we will get a straight oblique shock. So statement 2 says, a straight oblique shock can form on a curved surface, which accounts for the curved streamlines behind the oblique shock. So this is a true statement. We already saw. Now similarly, if we take a similar analogy, the curved shock will be formed on a straight wedge due to the non-equilibrium flow. Here you can see that as shock angle is decreasing, the velocity will be increases as we move away from the flow. Starting point of the wedge. And as the velocity will increase, then near to the body, this velocity will be equal to each other. So it is also possible that curved straight wedge will have a curved shock wave. So a curved oblique shock will form on a straight wedge. This is a true statement. So what will be the option? Option A will be the correct. Now we will see the other problem. Two 2D cylinders with nose radii R1 and R2 are immersed in two different hypersonic flow fields with free stream air density of rho 1 and rho 2 respectively. The T infinity and U infinity of these two free streams are identical. The bow shock formed ahead of the two bodies induces dissociation of O2 only. In the above context, choose the correct option given below if rho 1 equal to half rho 2. Option A, R1 equal to under root R2. Option B, R1 equal to half R2. Option C, R1 equal to 2 R2. And option D, R1 equal to R2. So what will be the correct answer for this? Okay, we will see the solution. So in this solution, we have to consider the binary scaling. According to binary scaling for hypersonic flow, if both are similar, identical, both are similar, then rho 1 R1 will be equal to rho 2 R2. And if you see from here, R1 equal to rho 2 by rho 1 R2. And rho 2 by rho 1 is what? Nothing but 2. So it will be equal to 2 R2. From here you can see rho 2 by rho 1 equal to 2. So the correct answer will be option C. Now we have seen the previous week 9 assignment problem. Now we will see some problem related to week 10. From kinetic theory of gases, the viscosity coefficient is dependent on the following. Choose the correct option. Option A, directly proportional to the number density of the gas particles. Option B, directly proportional to the mass of the gas particles. Option C, inversely proportional to the mean free path of the particles. Option D, inversely proportional to the mean particle speed. What will be the correct answer for this? Okay, we will see. So from the kinetic theory of gases, we found that mu is equal to 2k nm c bar lambda. So we can say mu is directly proportional to number density. Mu is directly proportional to n number density. It is directly proportional to mass of particles gas particles. It is directly proportional to c bar mean speed and lambda mean free path. So if we check the option 1 says that proportional to number density of particle, which is correct. Directly proportional to mass of the gas particles, this is also correct. Inversely proportional to mean free path of particles, this is wrong because it is directly proportional. Option D, inversely proportional to the mean particle speed, this is also wrong because it is directly proportional to the mean particle speed. So in this problem, only option A and B are the correct option. Now we will see the next problem. The following term in the high temperature compressible viscous reacting flow is distinct from high temperature compressible invisible reacting flow. Option A, dH upon dt. Option B, del dot B. Option C, dP upon dt. Option D, phi. So first we should know that phi is the dissipation coefficient function. So what will be the answer for this problem? Okay, so let's see the energy equation. Rho dH naught upon dt equal to dou P upon dou T minus del dot Q vector plus dou by dou x u dou xx plus dou y u tau y x plus dou y dou z u tau zx plus dou y dou x v tau xy plus dou y v tau yy plus dou y dou z v tau zy plus dou y dou x w tau xz plus dou y dou y w tau yz plus dou y dou z w tau zz. This is taken from lectures directly, where here h naught equal to h plus v square upon 2. If we write it in different form, then it will be dou rho dh upon dt equal to minus k del dot q vector equal to d rho dp upon dt plus phi, where phi is the dissipation function, and its value is given by phi equal to tau xx dou e by dou x plus tau yy dou v by dou y plus tau zz dou w by dou z plus tau xy dou u by dou y plus dou v by dou x plus tau xz dou u by dou z plus dou w by dou x plus tau yz dou v by dou z plus dou w by dou y. So if we compare it with the inverse compressible flow, the difference will be only in this term, phi, dissipation function. Why? Because it has this tau, xy, tau, xz and tau yz. So all these has viscosity in it. So due to the viscosity, this term is only present in viscous flow. So this phi term will be the only difference. So option D will be the correct answer. Now we'll see the next problem. Similarity parameters for a viscous chemically reacting boundary layer are option A, Reynolds number, option B, Prandtl number, option C, Lewis number, and option D, Eckert number. What will be the answer for this problem? Okay, we will see the answer. So if we write the boundary layer equation for energy, then we will get rho var u var dou h naught var upon dou x var plus rho var v var dou h naught var upon dou y var equal to 1 upon re pr e dou y dou var a var k var dou t var upon dou y var plus le upon re pr at e h dou y bar upon dou var d12 bar sigma hi bar dou ci bar upon dou y bar plus e upon re at h dou upon dou y bar mu bar u bar dou u bar upon dou y bar. Here all the quantity with bar are non-dimensionalized quantity, and this re, pr, le and e are non-dimensionalized number, where re is nothing but Reynolds number, which is given by rho e u e l upon mu e. Prandtl number pr is given by pre equal to mu e cpfe upon ke. Here cpfe is for frozen flow. The frozen flow Cp value is considered at the H. Lewis number is given by Le equal to rho e d12 e Cpfe upon K. This Lewis number is nothing but energy transport caused by diffusion relative to thermal conduction. And the last Reynolds uh, non-dimensionalized quantity is Eckert number, which is given by E equal to UE square upon HA. For the calorically perfect gas, the Eckert number is gamma minus 1 m square. So if we check for this calorically perfect gas, this E will be UE square upon HE. And what is HE? H is nothing but CpFe into Te, and it can be written as gamma upon gamma minus 1 R Te, and it will come as gamma minus 1 UE square upon this gamma RT is nothing but AE square, and it will give gamma minus 1 m square. So these four non-dimensional parameters are present. So according in the problem, if we check the option, these are Reynolds number which is present, Prandtl number which is present, Lewis number which is also present, and Eckert number which is also present. So all these four options will be the correct answer. Now we will see the next problem. For the boundary layer formed on a vehicle flying at hypersonic speeds, the following statements are made. Choose the correct option. The boundary layer formed on the vehicle can have regions of equilibrium, non-equilibrium, and frozen flow. The nature, equilibrium, non-equilibrium, and frozen of the flows depends on the time spent by the fluid particle as it moves through the boundary layer, and on the chemical reaction rates at a local temperature and pressure. When the vehicle flies at an angle of attack, the more dissociation occurs on the leeward side of the vehicle than on the windward side. Option A, if statement 1 false, if statement 2 true, if statement 3 false. Option B, if statement 1 true, if statement 2 false, and if statement 3 true. Option C, if statement 1 true, if statement 2 true, and if statement 3 false. Option D, if statement 1 false, if statement 2 false, if statement 3 true. So if we check the statement 1, it says that inside the boundary layer, region of equilibrium, non-equilibrium, and frozen flow can happen. So what will be the answer for this problem? So as I read this statement 1, it says that inside the boundary layer, vehicle can have regions of equilibrium, non-equilibrium, and frozen flow. So this is true because all these three possibilities are there. So this is the true statement. If we see the statement 2, the nature, equilibrium, non-equilibrium, or frozen of the flow depends on the time spent by fluid particle as it moves through the boundary layer and on the chemical reaction rates at the local temperature and pressure. So we already know that it depends on two times which are given by tau f, flow time, and chemical reaction time. And we already know that chemical reaction time will depend on Chemical reaction rates. So ultimately, the nature will depend on flow time and chemical reaction rate, which is true. When the vehicle flies at an angle of attack, more dissociation occurs on the leeward side of the vehicle than on the windward side. So let's say this is the vehicle. So if there is some angle of attack, then this side will be the windward side and this side will be the leeward side. And if there is hypersonic flow, then you can see that there will be one oblique shock, and here will be expansion fan. So due to the oblique shock, temperature will increase, and increased temperature will cause the more dissociation to occur on the gas, and expansion fan causes the temperature to decrease, which will reduce the dissociation. So on the leeward side, there will be less dissociation which will occur compared to the windward side. So this statement 3 will be the false. So true correct option is option C. Now we'll see the next problem. Choose the correct option or options from below in connection with radiative flow fields occurring at the hypersonic conditions. Option A, they are adiabatic. Option B, they are non-adiabatic. Option C, if the medium behaves like a transparent gas, then it emits and absorbs radiation. Option D, two basic quantities describe the transfer of radiation through a gaseous medium: radiative intensity and radiative flux. So what will be the correct answer? First thing to know that is that radiative flows are always in non-adiabatic. This H naught will not be constant. This statement does not look that good. So we know that there will be in non-adiabatic in nature always. So statement option B is correct and option A is wrong. If we the option C, if the medium behaves like a transparent gas, then it emits and absorbs radiation. This absorption part is the wrong thing. If it behaves like a transparent gas, then it will only emit the reaction. Whatever the reaction passes through will go through the body medium, it will directly let pass. So this statement C will also be wrong. And the two basic quantity which describe the radiative transfer, that are radiative intensity and radiative flux. This is the correct option. This is true. Now we'll see the next problem. Choose the correct option or options regarding stagnation point heating at the nose region of a blunt body with radius r. Option A, radiative heat transfer is directly proportional to r. Option B, radiative heat transfer is inversely proportional to r. Option C, convective heat transfer is inversely proportional to under root r. Option D, convective heat transfer is directly proportional to under root R. So what will be the correct answer for this problem? So the radiative heat transfer at a stagnation point for a blunt body. Let's say this is the blunt body and this is the Bofock and this is the lambda, sorry, delta, which is Fock stand-up distance. And this delta can be approximated by R rho infinity upon rho s. So this stagnation point heat transfer is given by E del upon 2, which is approximately equal to E by 2 R rho infinity upon rho s, where rho s is the shock layer density. Rho s is the density here and rho infinity is the density here, where E is the total energy emitted by gas in all directions per second per unit volume. And this E is equal to 4 pi J, where J is the energy emitted per second per unit volume. So from here we can see Q radiation is directly proportional to R, and similarly Q convection at the stagnation is directly proportional to inverse proportional to under root R. So the correct option will be radiative heat transfer is directly proportional to R and convective heat transfer is inversely proportional to under root R. So option A and C are the correct option. Now we will see one derivation. This equation was mentioned in the lectures, but the derivation was not told. It was given as a, you can say, homework. So sigma I rho I ui equal to 0. Its derivation. So let's say there is one slab of the gas which have the concentration differences. So there is one variation of Phi which varies with distance x, and its gradient will be positive in this direction, right hand side. So if gradient is positive in this direction, it means that here this side will be high concentration and this side will be low concentration. So flux of the species I will be from right to left. So this will be the direction of flux. And the mass flux of a species I is given by nothing but rho I ui. And from Fick's law, this rho I ui will be equal to nothing but rho dim del Ci, where this rho is the overall gas mixture density, dim is the diffusion of species I in the mixture. This is the equation 1. This is for the stationary. Now for the, if you see that this whole gas slab is moving to the left direction with velocity v, then what will be the vi of relative velocity? Vi means mass motion of species I relative to lab. It will be equal to velocity v plus ui. This is mass motion of mixture with respect to lab, and this ui is diffusion velocity of species I this is relative to mass motion of gas mixture. This is the equation number 2. And beside these, the velocity of the flow can be given by sigma Ci Vi. It is nothing but average of the velocity of all species. So this is the equation 3. So let's multiply Ci in equation 2. So we will get Ci Vi equal to Ci V plus Ci Ui, and we will take the summation of sigma for this. Sigma Ci Vi equal to sigma Ci V plus sigma Ci Ui, and sigma Ci Vi is nothing but V, and this V is the constant common everywhere, so it can come out sigma Ci plus sigma Ci Ui, and the sigma Ci is nothing but 1. So this V and V will cancel, and we will get sigma Ci Ui equal to 0. Now we will see the derivation of one more relation, which is Q radiative heat transfer at stagnation point is equal to E del upon 2. Its derivation. First, let's say there is this gas, transparent gas is there, and what is the transparent gas? A transparent gas let all the emission pass through it. It does not absorb anything. It only emits the radiation. And let's say there is point P here with area D, and at distance R, which makes angle beta from its normal, there is one volume, infinitely small volume dV. And J is total energy per unit solid angle per second and per unit volume. So energy emitted from dV energy emitted from dV which crosses dA per second, if it will be multiplication of J dV, which is nothing but total energy per unit solid angle. So we have to multiply it by solid angle to get energy per second, and that solid angle is nothing but dA cos beta upon R square. This is solid angle intercepted by dA. So integrating this whole energy and dividing by dA, we can get the radiative flux. This is nothing but energy per unit area per second. So it will be equal to Q equal to integration J cos beta upon R square d beta, dV for control volume V, and it can be written equal to 1 upon 4 pi integration v e cos theta upon r square dv, where E is nothing but total energy per unit volume per second. So we will use this formula to find the relative heat flux at the stagnation point. Before also one mistake I made. This is the radiative flux. This QRAD is the radiative flux. Now let's take a infinite slab which has the thickness of delta. This is a slab of gas, transparent gas. And there is one point where we have to find the flux, and there is one infinitely small volume dV which makes an angle beta, and it is located at distance r. So in spherical coordinate, dV will be equal to r square sine beta d beta d theta dr, not theta, d phi. So from the previous equation, we know that Q equal to E upon 4 pi integration E cos theta upon R square dV. We substitute the dV, one mistake. I used it 2 times D, but there is only D one time. So we'll get 1 by 4 pi integration 0 to pi by 2, 0 to 2 pi, and 0 to del upon cos theta. I will tell how we got this limit. Del upon cos theta, E cos theta upon R square into R square sine beta d beta d phi dr. This is the limit for R, del upon cos theta. So this length is del. So partly this length R at this end, it will be del upon this R will be equal to cos theta. So R will equal to del upon cos theta. Now this R square will cancel, and if we take the integration first with respect to R, then we'll get 1 upon 4 pi integration 0 to pi by 2 integration 0 to 2 pi cos theta sine beta and into R 0 to del upon cos theta d beta d phi. So if you put the value of del upon del cos theta and 0, we will get 1 upon 4 pi integration 0 to pi by 2, integration 0 to 2 pi del sine beta. I forgot the e, sorry, e will also be here, e. If e is constant, so it can also be taken out. So this e delta I will take it out, and I will get e delta upon 4 pi integration 0 to pi by 2 integration 0 to 2 pi sine beta d phi d beta. If we take the integration with respect to phi now, then we will get multiplication f phi 0 to pi by 2 phi sine beta 0 to 2 pi d beta. So we will get 2 pi here, so we will get e del by 2 integration 0 to pi by 2 sine beta d beta. Integration of sine beta will be minus cos beta. It will from 0 to pi by 2. Pi by 2 value is 0, and for 0 cos beta it is minus 1. So it will become e del by 2. For the stagnation point region, we can assume that this fog layer will act almost as a thin layer. So this is the approximate value at the stagnation point. So whatever theory I have taken is from the lectures and from the book Hypersonic and high temperature gas dynamics. Here I will draw the figure also. This is for the blunt body, and this is the fog, and this is the lambda distance. Then this QR at stagnation. QR at stagnation will be equal to E del upon 2. So we will stop here for today. Thank you.